In the lesson today, we're going to continue talking about how we can describe data sets, except with today's lesson, we're going to be looking at quantitative measures, where in the last one we were looking at visual displays of data. And in particular, we want to talk about what we would call measures of location. So in general, a measure of location is going to essentially be what values are typical in the data set. And so we're going to look at a couple of different ways that we can measure the location of a data set during today's lesson. The two main objectives that we would have is that when you leave the lesson today, you should be able to understand and interpret our mean, median, and mode of a data set. We also want to be able to understand and interpret what we would mean by a sample proportion. So these are going to be quantities that come up all the time throughout this course, and so getting a firm grasp on them now is definitely advisable. So to start, we can think about asking the question, where is our data? So if we're given a large data set, how do we understand where the observations typically fall, right? And so maybe to be somewhat more concrete, you could imagine rolling a die 50 times, right? And recording which face showed up on the die. And our question is going to be, what values are common? Where is our data centered around? What do we expect to happen when we roll the die? And you could sort of imagine a couple of different ways about thinking about this, right? And with a die, we're all familiar with it, right? And we know that there's not going to be one face that's substantially more likely to come up than any other face, right? And so in that sense, there's not really a center of the distribution, right? Because you expect to see a 1 about as often as you're going to see a 6. And so because of that, there's sort of no central tendency there. But you might think about instead, what is going to be the center if I sort of summed up all of the die that I was rolling? And if that's going to be the case, we know that sort of on average, you're going to be rolling 3.5 per die, right? If you add up the numbers 1, 2, 3, 4, 5, 6, divide that by 6, you're going to sort of get 3.5. So if you're summing the rolls of die, each one's going to contribute sort of a 3.5, right? We know that in 50% of cases, you're going to roll less than a 3, and in 50% of cases, you're going to roll more than a 3. And so there's another way that you might think about the data sort of being centered around. And so all of these different ways are ways that we could think about measuring where the data that we land are. And it sort of depends on context as to which one's going to be most relevant for us. So if we actually looked at sort of the plotted histogram there, you can sort of see those different things that we were talking about, right? In this case, a 2 or a 3 were the most common rolls, but not substantially so, not a lot more than we would expect sort of from random chance. But you can start to see through the histogram all of the other points that we were just looking up there. There are really 3 different measures of location that we want to think about using on a sample. And the first one, the most common one that you're probably familiar with, is the sample mean. In sort of day-to-day parlance, we're just going to call this the average. And it's what you'd think about if we talk about an average. So the idea with the sample average or the sample mean, is that we're going to add up the total of all of our observations and divide by our sample size. So just as a brief review of our notation here, remember that n is our total sample size, xi denotes each observation, and so then what we would say is the sample mean, which we denote by x with a bar over it, or x bar, is going to be 1 over n times by the sum across the whole data. So it's what you think about as the average. We could also think about doing the sample median, right? And this is going to be the halfway point of a data set if you were to order the data. And so this is going to depend on whether we have an odd number or an even number of data points, right? And so if you have an odd number, there's some exact middle of your data, right? And so you just order them all up, and then you'd say, what's the middle value here? If you have an even number, well, then there's not going to be exactly a middle point, right? And so instead, what we would do is take the average between the sort of middle point and the one-off middle point, right? Sort of the 2 points around the middle. So in the case of looking at the sort of theoretical median of our die roll, right? We know there's an even number there. So 3 and 4 would be our 2 middle values. So we would take the average of those. 3 plus 4 over 2 gives us our 3.5. And the nice part about a median is that it sort of captures the idea intuitively of what we might think of when we're thinking about an average, right? Half of it's going to fall below, half of it's going to be above, and normally that's sort of the way people think about averages. So often medians are quite nice to think about, but sample means come up all over the place, and they're very useful anytime that we're thinking about summing up. The last measure of tendency, it's also the one we're going to think about the least in this course, is the sample mode. And for the mode, it's just going to be the most common or the set of most common observations, right? So if you observe a 10 more often than any other number in your data set, that's what the mode is, right? And there are times where the mode's going to be a very useful measure for us, but generally speaking, we think about the mean or the median as sort of better capturing the underlying truth. Now, because the mean and the median are the two measures that we tend to use, we're also going to be sort of most concerned with comparing them. And the first thing that we can say is that if our data are approximately symmetric, the mean and the median are going to be similar, right? And so it's not going to so much matter which one you choose if you have symmetric data. However, if the data are skewed, then what we see is that the mean is going to be pulled towards the longer tail of that distribution, right? So if you have a really long positive tail, if you have sort of right skewed data, then what you're going to see is that the mean is going to get pulled up into that tail, sort of away from where the bulk of the distribution is. The same is true sort of in reverse. And so because of this, what we do, or what we say, is that the mean is going to be more sensitive to skewed outliers than the median is, right? And so if we know that the data are skewed, the median is probably going to give us a better picture of what our true sense of the center of the distribution is. The really common example of this is if you're thinking about incomes, right? And so we know that for incomes, most people sort of earn in a particular range. Say, almost everyone is earning less than $200,000 a year as a family. But there are some families that are going to be earning, multiple millions of dollars every year, right? And so if you think about how we're calculating the sample mean, right, by adding up their very large incomes, and then still off dividing by the same n, what we're doing is we're pulling up that mean. And so if you look at the mean income, it's going to be a lot higher than the median income, even though the median income is probably the thing that we actually want. Generally, when we have skewed data, we're going to prefer the median. That's not always going to be the case, but the median is typically a safe bet. So we can see some examples on those histograms we were looking at last time. So we have a symmetric distribution. We plot the mean as a dotted value in red, the median in blue. And you can see with this symmetric distribution, the mean and the median sort of line up exactly. When we have this positively skewed data, the mean, which is the red dotted line, is getting pulled above the median. And if we saw some negatively skewed data, then we're going to have the mean pulled below the median. You can see when we had this rather symmetric distribution before, again, the mean and the median are quite close to one another here. And I would say that the differences between these two are almost certainly attributable to just sort of random noise, right? But you can see that it's sort of the same type of pattern in this symmetric distribution here. The uniform distribution is the same thing as well, right? So there's no sort of skew here, so the mean and the median are going to overlap. You could pick either one. They're going to be equally useful. Now, a really important point that I want to stress. People often say that the median is resistant to outliers. And that's true. However, it's not just outliers that we care about, right? So if we look at this distribution here, you can see that almost everything is between -1 and 1. But then we have a couple of values that are up above 4 and a couple of values that are down below -4. And so we have really large outliers here, right? Like those 4s and -4s are huge compared to the rest of the data. And yet we can see that the mean and the median are perfectly aligned. And that's because the distribution is still symmetric, right? If you mirror this, you still get it. And a mean is not going to be impacted by symmetric outliers. If you have really big and really small values, then the mean is still going to be approximately equal to the median. So remember, it's not just the presence of outliers that are important for determining whether you should use a mean or a median. It's about the skewness of the data. If they're heavily skewed outliers, that's where the median is going to start to be more robust. With categorical data, none of this is going to work, right? We don't have data that we can add up. We can't consider what sort of the most frequent occurring value is. And so instead, what we want to do is think about sort of the relative frequencies of each of the categories. And what we use for this is called the sample proportion. So if we assume that there are k different categories and that we have several different observations, and I guess in this case, it probably would have been smart to use a different subscript other than k, right? So we don't need to have the same number of categories as there are observations. We could say that we have C1, C2, say up to CL, and then we have X1 to XN observations, right? And N does not have to be equal to L. Maybe it is, maybe every single individual is in a different category, but those two things don't actually have to be equal to one another. And then what we're going to do is define this indicator function, right? So Zij here, Zij is going to take on a value of 1 if Xi equals Cj, and it's going to take on a value of 0 otherwise, right? And so in this way, what we're doing is we're converting these categories into a set of different binary variables, okay? Then what we can do is we can take the sample mean for each sort of category j, and we define that to be the sample proportion, right? So then we would have P1, P2, all the way up to PL. And thinking about that sum, right, each Zij is going to be either a 1 or a 0, and then we're dividing by the total. So this is just the proportion of the data that falls into each of our different categories. And when we're dealing with that, we call that our sample proportion. You could think about, for instance, looking at those rolls of the die earlier. Here now we have 100 of them, and if we wanted to know what's the sample proportion for category number 4, what we do is we count up how many 4s there are, right? And so we can see there are 20 different 4s once we've counted them all up. And so then we would have 20 out of 100, or 0.2 as our sample proportion. You could get to this equivalently by going through and saying, is this a 4? And if it's not, it gets a 0. And if it is, it gets a 1, right? And so in that top row there, we'd have a 0, 0, 0, 0, 0, 0, and then a 1. And if you do that for all of them, and then you add them up, you're going to be counting the number of 4s, divide by the 100, that gives you our sample proportion. So generally speaking, measures of location are about what usually happens in a data set. We can think about doing the mean, the median, or the mode for quantitative variables. The mean and the median are the most commonly used. We prefer the median if the data happen to be skewed. And if we're dealing with categorical variables, we can summarize the location using the sample proportion for each of the different categories. So that demonstrates sort of one way of summarizing the data quantitatively. In the next lesson, we'll look at a different way that we can start to talk about the distribution in a quantitative manner. And so I will see you all in that next lesson.